two kinds of uncertainty, as I've urged in the past. One is uncertainty in the sense of incomplete information, but the other is the dual uncertainty in the sense of contradictory information. There's sort of too little information, there's too much information. If we've ever used the World Wide Web, I'm sure we have, we know the danger of inconsistency. I think it's actually affecting our political process. You can pick and choose, right? Get whichever side you want on an issue. And so I want to urge that I think we need to develop systems where contradictory information can be dealt with just as seriously as incomplete information. And I developed a little bit more about my work, but I presented once a so-called opinion tetrahedron, which was a four-valued way of looking at subjective probability theory. So instead of just the extremes of 1 and 0, you could also have the extremes as of truth and falsity, sort of absolute truth, absolute falsity, certainty. You could also have degrees of information coming in that would lead to too much information and too little information. And out of all that, you can construct, modifying the construction Alden Yosang did for the triangle, the opinion triangle. He called, I had the opinion tetrahedron. Now, one more slide, I think. Information emphasized in Shannon's terms, communication. Well, I want to ask, if a tree fell in a forest and you were there, would it give you information? There is no sender, right? Now, I know a number of people are working on information in the context of physics, biology, economics, and so on. Economics involves people, but physics and biology need not involve people in terms of sender and receiver, at least. And so the question is, must there be a sender? If a tree fell in a forest with no one around, it would still make a sound. Would it still give information even if there is no receiver? So those are some questions to ponder. One more political joke. If the tree fell in the forest with no one around, it could still make a sound. If somebody found a way to link it to Hillary. Okay. So that's my spiel, my 10-minute elevator talk. Maybe too long for an elevator talk. But now I guess what's next?
Richard's next.
Richard.
Actually affects the process of doing causal discovery. So I'm going to wave my hands and go through some basics extremely fast. Forgive me if this is all unfamiliar to you. But nearly 30 years ago now, maybe even more, there was a really big revolution in this field in which causal structure, causal hypotheses could be in very general way connected to statistical sort of ideas with this idea of the causal Markov and the deseparation assumptions. So if you have a causal graph, which is a completely qualitative idea, you could connect that to a completely qualitative idea in probability, which is independence and conditional independence. So we have this bridge getting from causal structure to probability, and we can get predictions about what relationships in terms of independence and conditional independence should hold, right, in data produced by causal structures. And because we could do that, we could go the other way. If we have data and we can make inferences about what's independent, right, we could build these algorithms that would compute all the structures that would make those predictions, right? And what you get is not a single graph or a single causal structure. You get an equivalence class of all the structures under a certain set of assumptions that would make those predictions. So then the question was, for me, well, what happens if we actually lose information about some of the variables in the system we're trying to discover? And just the way I thought my way into that was, if I have a simple system like x, z, and y, where z is separating x and y, and we know that we have this conditional independence, that x and y are independent given z. But if we have a measure of z in which we've lost information about it, I'm calling it z prime, right, so that, you know, z prime is equal to z plus some random noise, right, which is a sort of a classic measurement error kind of understanding. Well, it turns out that under those conditions, x and y are no longer conditionally independent if we condition on z prime as opposed to z. So this sort of information loss loses conditional independence, which is sort of killing, right, in causal inference terms. There's another situation which is also an interesting thing to worry about, which is not measurement error, but coarsening, right? So if I have these asterisks, which is some projection of a continuous quantity onto a discrete set of values, I'm going to have essentially the same problem, right? So where x and y are independent on z, they're no longer conditionally independent on z star, almost all the time, unless you have this very lucky sort of projection. So I take those to be the sort of the two problems that really motivate causal discovery and how it reacts to information loss. And it turns out we know an awful lot about it in local contexts. So here's a situation in which I have x in the circle, and it's causing y in the circle, and z is a covariate or a confounder, and my task might be to estimate beta, right? What's the coefficient that actually parameterizes or tells you the strength of the causal relationship. And the variables in the box might be those sorts of measures of each of those things, right? And those might be measures with error, or there might be coarsenings of those variables. So we know an awful lot about what happens to the inference about beta in this kind of situation. So if we have a noisy measure of the effect y, right, we still get a good estimate of beta, but its standard errors inflate. If we have a noisy measure of x, we can get a good measure of an estimate of beta, but it attenuates towards 0. If it's negative, it goes towards 0. If it's positive, it goes towards 0. And if we have a noisy measure of the confounder, right, it's like partial emitted variable bias. And we can handle all of those situations, right, with a variety of strategies. We can do instrumental, we can do sensitivity analysis, we can do a Bayesian analysis on what measurement error looks like. So there's lots of good information to be had. But the problem with causal discovery is that the effective independence decisions on the process of discovery is highly non-local. And so what we're doing when we're actually applying a discovery procedure to a set of variables is making a sequence of independence decisions. And each independence decision has a quite global effect on how we reduce the search space in terms of the set of graphs. And so the strategies that we can employ in this kind of a setting, right, don't translate well to a discovery procedure. So here's a simple example that I think illustrates the point. So if here's my true graph, and I'm looking at all these variables, L1, L2, X1, X2, X3, and X4, and only 2 of them are measured with error, L1 and L2, the ones in circles. And everybody else is measured perfectly, right? If I have a parameterization of that in which, right, this is a standard structural equation model, all the relationships are linear, and the measurement error I impose on L1 and L2 in the first case is extremely small, very negligible, only maybe 1%, right? Then when I apply a causal discovery algorithm to the measured variables that I'm shown on the right here, I get pretty much all I could get from the information in those variables. You'll notice that the connections of L1M and X1 are undirected, so I get the right adjacency, but I don't have the orientation. So if I only have a small amount of measurement error on those 2 variables, I can do really well. But if I crank the measurement error up on just those 2 variables, right, the output becomes total disaster. So this is the output of what's called the fast, greedy search algorithm, right, on the same variables, but now I've cranked up the measurement error to 20%, which is still not a lot, given the context of research, I think, that's typical in economics, typical in social science, et cetera. But you can see this really alarmed me. This really freaked me out, because this is a huge, huge problem in terms of the output. So I did this small study with a colleague of mine, Joe Ramsey, in which we sort of looked at the effect on the algorithm's accuracy, right, on imposing various levels of measurement error on all the variables in the system. And we measured the accuracy in 4 ways, like typical machine learning kind of measures. We did the adjacency precision. What is the proportion of correct adjacencies among those that are conjectured? The adjacency recall. And then the arrowhead precision. What's the proportion of correct arrow orientations, right, among those conjectured, et cetera. And then we did a simulation. We took 20 variables, constructed a random graph. In some cases, we had the average degree of the nodes be 2, so that the average number of connections they're involved in was 2, very sparse kind of graph. And then in some, it was 6, so it was a more dense graph. We varied the sample size, and we varied the amount of measurement error quite a lot. So here were the results. On the x-axis, we have sample size, and it goes up from about 50 to about 5,000. On the left, you have all the simulations with a sparse graph. The average degree is 2. on the right the average degree of 6. And so you can see that when the sample size gets to even around 1,000, the algorithm is extremely accurate, right, on average degree of 2. And then on average degree of 6, it takes a much larger sample size, and things don't really ever get incredibly perfect, even in sample size of 5,000. So this is in a context of 0 measurement error. So this is sort of a baseline, right, of what you could do. Now, this is what happens, right, if you have small amounts of measurement error. So now signal to noise, right? You're gonna
Yes.
you're gonna have to.
I was thinking that.
So you can see that on the very far left of each of these graphs, on the top is sample size 100 and the bottom is sample size 500. We're dealing with 0 measurement error, and then as we move to the right, I've increased the amount of measurement error on all the variables, right? And so by the time you get to even, right, 0.2 or 0.3, you get a severe decay in some of the measures of accuracy. And the x-axis measurement is a little bit unfortunate. 2 is essentially meaning you're at totally 50% of the variables. Variance is just noise. And here are some more general pictures. The upper left and the middle are the same pictures I just showed you. Now, on the right, are the situation when you have an average connectivity of 6 as opposed to an average connectivity of 2. So every situation in average connectivity of 6 makes things worse. And then as I go up with sample size and I look at, the measurement error of 0.2, 0.5, 1, and 5, I can also see how, things affect the algorithm's accuracy. So I take this to be the beginning of a project that for me is exciting going into the future, but the sort of the moral of the story for me is that when you have a complicated procedure that takes a sequence of decisions, and each decision might have non-local global impacts on the accuracy of the procedure, there really is no analytic way to deal with that, because the situation is so complicated combinatorially, and what might happen with errors are so complicated that I don't have any idea how to even think about dealing with analytically how these kind of information loss situations affect the overall accuracy. So simulation was the way I went, and I think we can learn a lot from it. But I haven't even begun to think my way into how things work in the same context with coarsening as information loss and other things. But I think in general, for the future of information, it would be great to have people work more on how information loss affects complicated procedures that actually, can't be characterized in some local way. Thank you, and thanks again for having me.
Okay, I would like to present the information theoretic approach based on physical-chemical rules to the studies of biological phenomena associated with cancer pathology. So cancer is a disease that results from the acquisition of the genetic alterations, leading often to the changes and rewiring in protein-protein interaction networks. Proteins are the machines which execute in the real time the main biological functions, such as cell growth, cell division, cell communication, and more. And protein-protein interaction networks actually define the organismal phenotypes or organismal characteristics. In cancer, those protein-protein networks undergo usually rewiring in a very patient-specific manner, leading to patient-specific responses to the therapies, highlighting therefore a personalized treatment or an urgent need for personalized medicine. For example, here, two other proteins which can actually function in a different process. Thus, the precise resolution of the protein-protein networks in cancer is required. So many analytical methods have been developed, such as Bayesian method or clustering methods, principal component analysis, single value decomposition, and more. But despite an enormous progression in the field of data analysis and also cancer research, aggressive tumors still do not respond well to the therapies, suggesting that our understanding of the protein interaction networks in cancer is still incomplete. Physical approaches, such as thermodynamic-based approaches, may overcome this gap by suggesting rigorous and solid theory which can be valid for each single patient. Moreover, those theories can allow us to predict a change in biological processes. So we suggest to use thermodynamic-based information theory. Information theories have been successfully applied to several cases in biological research. Those approaches rely on the concept of statistical entropy. So, of course, if entropy is low, one state or a few states stand out, and the information about the system is provided, in turn providing the knowledge, for example, knowledge about protein-protein interaction networks. And in this way, we can distinguish between different states of the biological system. So to analyze the system based on physical rules, we need to rephrase statistical entropy by physical entropy. And to do so, we suggest to use thermodynamic-based information theoretical surprisal analysis that allows us to identify from the experimental protein expression levels the steady state of the system and deviations thereof. The steady state in biology is a state in which all the inputs and outputs are balanced, and intermediates are consumed and generated at equal rates. And this is actually the most natural starting point for applying of the thermodynamic-based principles. So here you can see the steady state is actually the light gray color. And also we identify the constraints that prevent from the system to reach the most stable steady state. So we recognize in biology the constraints by identifying how the experimental protein expression levels deviate from their expected levels at the steady state. Thus, in biology, constraints actually are unbalanced processes operating in the system. Here you can see those unbalanced processes in black. So our hypothesis is that through simultaneous inhibition of the central proteins in distinct unbalanced processes will reverse actually the signaling imbalance and will restore the steady state in the tissue. So I will give you like two simple examples. Actually, we validated the theory recently. For example, to study the infiltrative nature, and I presented it recently in our previous workshop. So to study the infiltrative nature of brain cancer tumors, in which actually the cancer cells spread out within the brain, we developed an approach based on two cell interactions. So to measure the central proteins involved in cell-cell communications, we used a chip that allows us to isolate hundreds of brain cancer cells in small microchambers. So in those microchambers, we measure the protein expression levels as a function of cell-cell distance. So using the information theory and experimental protein expression levels, we could identify the distance range in which the constraints or unbalanced process do not operate. So, and actually the state of the system was the steady state. So we predicted that this distance range, which was around 90 micrometers, as you can see here, should appear with higher frequency in the bulk multicellular cultures. And as you can see from those two plots, the most stable cell-cell separation distance range, as identified in two-cell system, corresponds to the most probable cell-cell separation distance range in bulk cultures, multicellular cultures. We validated this approach in different cell lines. Also, using the same approach, we could precisely identify the soluble factors or proteins secreted by the cells that induce cell-cell movement towards the most stable steady-state separation distance. To show actually that those proteins create cell-cell potential that induce directed movement toward the steady-state cell-cell separation distance, we plotted a change in cell-cell separation distance in different time intervals. So here you can see the example for the distributions of cell-cell displacements that occurred after the incubation of 6 hours. So here we can clearly see that actually cell-cell movement can be described by a Brownian motion that corresponds to this Gaussian part, biased by cell-cell potential that was created by those secreted proteins involved in the unbalanced signaling process. So inhibiting the main proteins involved in the unbalanced process resulted in the inhibition or reduction of the directed cell-cell movement, but hardly affected the Brownian part. So now, using the similar approach, we aim to analyze large data sets that include cancer patients. And the idea is to identify those large data sets, the unbalanced processes operating in the whole population, and then to identify for each single patient a set of unbalanced processes. We call those sets codes. And then according to those codes, to design patient-specific therapies. So recently we analyzed a very big data set that included around 3,500 different tumors from around 10 different types of cancer, which were like brain cancers and breast cancers, head and neck, and more. And actually, this huge data set, which included very heterogeneous set of tumors, could be described by only 17 unbalanced processes. And the example for 3 of those processes can be seen here. For example, process 1, 3, and 5. This result is very important from 2 aspects. First of all, it's in line with the high degree of heterogeneity that can be seen in this data set, because 17 unbalanced processes can be assembled in thousands of different combinations of the sets from 1 to 4 unbalanced processes. The second point is that it simplifies actually the therapeutic approach, because now we need to find 17 different drugs and then combine them. Yeah, I'm finishing. And then to design different combinations in a patient-specific manner. So for example, here you can see example for 2 groups. And one group possess actually a code A, which is a set of 2 unbalanced processes, the process 1, 5. The second group has a code C, which is a set of the process 1 and 3. So now, according to those codes, we design patient-specific drug therapies. So I don't have time anymore, like for 2 more sentences. Okay, so what we actually we saw that out of thousands of different combinations that can be chosen out of 17, and actually we have more than 3,200 different combinations, what we found that only 420 codes repeat themselves in this population. More than that, only 15 are abandoned. They are shared by 15 patients or more, and around 380 codes are very rare. They're shared by only 5 or less patients, highlighting again an urgent need for the personalized medicine.
I want to thank Amos for doing something that takes our mind off the election for at least one day. Yeah, really appreciate that. Despite your efforts to bring it in. Okay, so
all being hacked while we talk.
So I want to talk about information theory as a foundation for theory building, and in particular, theory building in ecology. Ecological complexity is extraordinarily complex. I show on the screen 7 dimensions of ecological complexity, and I'm going to talk about the top 4, not the bottom row today. And in fact, I'm mainly going to talk about the upper left. But I want to emphasize that when ecologists look at community complexity, like the distribution of abundances of trees in a forest, or the dynamic response of ecosystems to disturbance, or food webs, or phylogenetic complexity, which is shorthand for evolutionary historic complexity, they invoke hundreds of mechanisms. They don't agree on which ones are important, but the problem of ecology is that we have a myriad of mechanisms and we don't have any basis for understanding which are more important and which should be used for building models and theory. So information theory provides us a way of bypassing the question of what are the particular mechanisms that we should hook together in a model. And I want to explain very, very briefly how that's done. I want to just get the one point across right at the outset. There are numerous metrics of pattern in ecology: species area relationships, abundance distributions, spatial aggregation measures, distributions of body sizes across individual organisms in an ecosystem, relationships between abundance and body size. And we see over and over again, when we look at real ecosystems, systematic patterns showing up over and over. So it begs for some fundamental level of understanding. The maximum entropy theory of ecology, which my postdocs and grad students and I have developed over the past almost decade now, is an application of information theory, inference, a top-down approach in which we specify at the macro scale certain constraints, which will go into a maxent calculation. The constraints are what we call state variables, which are quantities like the total number of species in the system, the total number of individuals in the system, the total metabolic rate of activity in the system. Those are the macro scale variables, and we want to predict with maxent the micro scale probability distributions, the distribution of abundances over species, body sizes over individuals, species diversity across space. The architecture of the simplest example of the maximum entropy theory of ecology is shown here, where metabolism is allocated to individuals and individuals are allocated over species. There's no reason not to extend that further to the left and allocate species over genera, genera over families, families over class, and so on. But this is the basic idea. Amusingly, the acronym MEET in English is MEET is another word for to allocate, and it is a theory of allocation. just to give you the snapshot of how the theory proceeds, I'm not going to go through any of the details, but Maxent gives two fundamental functions. The one on the top left, R, it's the ecological structure function, and it's a conditional probability over abundance and metabolic rate, conditional on the state variables, the number of species, number of individuals, total metabolic rate. And the other function is what we call pi. It's a spatial aggregation function. Maxent gives directly the forms of those two functions, and then from them, by integrating over metabolic rate or summing over abundance or combining functions with Bayes' law, we get all the metrics of macroecology, the species abundance distribution, metabolic rate distribution, species area relationships, and so forth. I'm not going to tell you the details. I just want to say that we have carried out now close to 2,000 tests of theory with real data. We've looked altogether at 30,000 species and 100 million individuals in 25 distinct habitats. I've got to put on my glasses. These habitats include desert, forest, Arctic, tropical, and so forth. And I'm not going to go through the tests, but in all the ecosystems we've looked at that are what we would call quasi-static, where they're not undergoing rapid change because of disturbance or ecological succession or rapid diversification, for example, after a major extinction event, what we see is excellent agreement with the predictions of the theory. But in systems that are rapidly changing, we see very systematic patterns of failure of the theory. And so the next step is to extend a quasi-static theory into the dynamic realm. And very briefly, the approach we're taking to this is to start out by introducing some explicit mechanisms, something I was reluctant to do, but it's a first step in eventually getting to a dynamic, non-mechanistic, purely informational approach, as you'll see. In this intermediate step, we write a master equation, assume a Markov process in which birth, death, growth, and speciation and extinction are the drivers of ecological change. And we derive a probability distribution for the state variables, and it will be time dependent. Then we use Bayes' law to combine the probability distribution of the state variables. This is it should be labeled number 2. I don't know why it's 1, 1, 2. It should be 1, 2, 3. Number 2 is we combine the probability distribution over the state variables with the structure function.
They can't see if you
They
point.
can't see if I point.
I do that exact same thing.
Right, okay. So this equation, we combine the probability distribution with the structure function to get the time-dependent structure function. And then we can derive from that, using that same chain of mathematics that we used here, to get the time-dependent metrics. Now, this raises the question, where do the transition rates, these mechanisms, birth, death, growth, et cetera, come from? And to look at this, we're now taking a bottom-up approach to an inferential procedure where we maximize log W, log of the number of microstates, to get and maximize entropy that way. I'm not going to go into the details, but what it does is it predicts the functional forms of the transition rates that went into the master equation for the dynamic extension of the theory. So we are now deriving the mechanisms from a bottom-up application using maximization of the log of the number of microstates. Now, we can put that together, and in our the dream we have of a future purely statistical theory of ecology is that we have a master equation for the transition probabilities, but I'm sorry, for the probability distribution of state variables driven by transition probabilities, which come from Boltzmann dynamics. And the input to the Boltzmann dynamics is the output from the traditional maxent, maximizing minus sum p log p. And so we get a logically consistent, we hope, theory of ecology that makes no ad hoc mechanistic assumptions. Final slide is my philosophy, and this would be a very controversial thing to present to ecologists, but I want to try it out on you. Maxent is a powerful framework for complex systems theory if, I believe, the system can be partitioned into macro and micro levels of description. And I think that's the critical thing. In ecology, we have state variables at the macro scale, and we have probability distributions of abundance and body size and so on at the micro scale. In economics, at the macro scale, we have population size and GNP and other variables. And at the micro scale, we have distributions of income over people or employment by job sector. Now, if we look at something like turbulence, which I believe is it's a really truly complex system because it can't be broken down into a macro and a micro scale with no continuum of scales in between. And so in turbulence, I don't believe this approach would make sense. But any system that can be divided into macro and micro, I think is fair game for this kind of information theoretic approach. Second point under philosophy, I believe that an obsession with causality and mechanism has hindered progress in understanding complex systems, at least in ecology. 3, ecosystems are what they are because anything else is much less probable. And that's particularly is an abhorrent idea to many of my colleagues in ecology. Finally, there is a role for mechanism, just as in van der Waals forces emerge when PV, because it leads to a breakdown of PV equals nRT. Similarly, we can begin to understand truly essential mechanisms in ecology by looking at situations where the purely inferential approach breaks down. And I think that's sort of a way to eventually discern whether indeed there are essential mechanisms or whether inference can do it all. And I don't know the answer to that, and I'm eager to find out. And the only way to do it is to push the inferential approach as far as it can be pushed and see what's left over at the end. Thanks.
All right. Well, thank you for your kind introduction earlier, and thank you, Amos, for having us. Oh, thank you.
So much for that.
See if I move this up higher, maybe that'll help a bit. Oh, it's just recording. Okay. So all right. So I'm very interested in the laws of physics. Of course, in our training when you go to school, we learn the laws of physics, and what's they're traditionally thought of as the laws of nature. This is the rules by which the universe is run, and people often think of the laws of physics as these are the rules that are decreed by Mother Nature. This is how things are supposed to work, and I'm not sure that's true. I'm not sure that's the proper way to think about it, and I think that your work is a good example of this. You're not talking about the laws of ecology, rules that govern how ecology works, and I think that the physics of the last century really points to this in some interesting and unique ways. We had the revolutions of relativity and quantum mechanics, where the role of the observer becomes very important. And that's very curious. Why should the observer be so important, to be so central? And there are little problems that have crept in. Quantum mechanics is weird. People don't like it when we say that. I've written a paper on derivation of quantum mechanics, and we actually wrote in the introduction that quantum mechanics is strange, and the reviewers objected to that. I'm sorry, it's strange. It's strange when you first encounter it. And there are some very difficult concepts that one has to grapple with. And what usually happens is you just accept them and shut up and calculate. And that's the way I was raised. But you have problems where a particle can't have simultaneously can't have a particular momentum and a particular position. All right, that seems very odd. That's one of many things that are odd about quantum mechanics. So why is this? And when you look at the role of the observer, and you think of special relativity, different observers moving at different velocities relative to an object will see the particle having different momenta and different energies. So is it really appropriate when we look at something, we say the energy that this possesses an energy E, and it possesses a momentum P. Well, does it really possess an energy? Is energy something that an object possesses? How can that possibly be if it's different for different observers? So some of our thinking is not quite right. And I can't help but think that if some aspects of our thinking isn't right in physics, this is going to spill over into other aspects of our thinking. And probably the most obvious problem in physics is that of quantum gravity. Quantum mechanics and gravity just don't get along. And this hasn't been resolved for 80 years. 80 years is a long time for people to be wrestling with a problem. I once had somebody say to me, that I objected to something that somebody had written, and they said, well, how can you object to that? This guy's an expert. He's been working on this for 25 years. And I said, he's been not solving the problem for 25 years. That I don't see that as impressive. And so there are problems with physics, and quantum mechanics is one of them. So it was announced very early on in the 1930s. Owen Garrett Birkhoff and John von Neumann looked at quantum mechanics. They basically said that the rules of inference in quantum mechanics is not commensurate with classical probability theory. It's a different kind of inference, and this has actually been carried on and amplified through these ideas of quantum computation, and that the inferences, the rules of inference that apply to quantum mechanics are thought to be different than the rules of inference that apply to everything else. Well, wait a minute, that's kind of odd. Why is it that we use one set of rules for making inferences with one set of things, and we use a different set of rules of inference for making inferences about a different set of things? That's curious. You ought to explain that. You ought to know what the difference is, because if that's the case, then there may be other subsets where you might have to have different rules of inference still, and we're going to just keep running into problems. I don't actually think that's the case. I think the rules of inference ought to be universal. And so there's some difficulties with this. The role of the observer is actually very important. And this idea, wondering whether an object can possess an energy, I think is something worth thinking about. If the energy of an object varies according to the observer, then the energy can't be thought of as something possessed by the object. The energy represents the relationship between the object and the observer. And so the energies and momenta have to do with relationships between things. What kind of relationship? We don't know what energy is, and momentum, and really, we don't know what these concepts actually represent. So it suggests that maybe there's a more fundamental layer to physics from which concepts like energy and momentum might be derived. The other interesting aspects that have come into play is the fact that black holes have entropy. And you can talk about the entropy of a black hole is proportional to its surface area. So information plays a very important role in physics. And this was summarized by John Wheeler's aphorism, it from bit, the idea that physical reality derives from information. I think it's a very nice idea, and I like it very much. And it really highlights the importance of information in physics. Although I think it's been carried a bit too far. You have some people saying the universe is information, or the universe is a computer. I think that carries it a bit too far because information is always contextual. Information's about something. And when you just say the universe is information, you're neglecting the fact that that information has to be about something else. And so what is that something that the information is about from which our physics is derived? I think that's a valid question. And so I think that's motivated a lot of my work in theoretical physics. And so I don't necessarily think of the laws of physics as being laws decreed by Mother Nature, governing how the universe works. I think of them being much more related to the laws that describe how to make optimal inferences about the natural world. At the University of Albany, we're all very interested in this. My friend and colleague Ariel Katica also works with physics and information. We have different views of this. I've become more interested in what this underlying layer actually is. How do you come up with a more fundamental theory that gives rise to things like space and time and energy momentum? Where could that possibly come from? So some time ago we decided let's step back and just come up with a really simple model, incredibly stripped down model of things you might be interested in. So imagine that there's particles, objects, they somehow influence each other. And we assume that this happens in a discrete fashion. And when one particle influences another particle, this allows you to define two events. There's the act of one particle influencing, and then there's the act of the other particle being influenced. And because they're different, you could order them. So that actually allows you to generate what's called a partially ordered set. And we decided to see what happens if you are an observer and you have some instrument and you're basically looking at a particle and all you can detect are these events. You can basically just see the events happening, you can count them, but that's basically it. How then do you describe this network of particles influencing one another? And it was very interesting because we were able to show that there's a unique way to describe them, and this gives you the mathematics of spacetime. You can actually drive the mathematics of spacetime this way. So I'm just going to use this to throw up a picture or two. This should have it. So we have numerous papers at this point, but there we go. So the idea here is that you may have a particle that you're tracking with your instrument. You see, here it is, there. And you may have two events, and these events may have influenced the particle that you're tracking, so you can detect those events. And now the idea is how do you quantify the relationship between the events A and B? And this basically you can track. You can basically number these events. And you can show that the unique length squared, a square of a number that you can assign to that interval, is basically a product of the lengths you record on your observers. So this is assuming you have two independent observers. This allows you to define something like time. Time is basically the average of the projections. Space ends up distance is the half difference between the projections. And this gives you a Minkowski metric in relativity. So you can get this idea of space-time comes right out of this network, which is very nice. The other thing that's interesting is you can, instead of looking at intervals and trying to quantify intervals, you can think of a particle that's influencing your observers or influencing others, and you can describe this particle in terms of the rates at which it influences others. And it turns out that the average value of the rates gives you the energy, the half differences give you momenta, and that these are Fourier transform duals of space and time, like you would expect from quantum mechanics. So you get an idea of energy and momentum this way. One of the more recent exciting things that we've been working on is we realized that if a particle is influencing others and is doing so at a certain rate, which gives it an energy and momentum, then this energy and momentum are observer-based because those rates depend on what the observers are detecting. So a different observer will detect different energy and momenta. So literally, the energy and momenta in this picture are observer-based, and they describe the relationship between the particles and the observers. Now, if somebody comes along and starts influencing this particle while it's influencing the observers, those influences are going to mess up those rates, which basically will change its energy and change its momentum. Well, if you change something's momentum, that's a force. So influences should act like forces. And so my current graduate student, James Walsh, is studying this, and he's basically shown that in that case, when a particle's influenced rarely, the particle is observed to, the observers would describe it as accelerating relativistically. So indeed, yes, it accelerates when you influence it. And he actually has now obtained geodesic equations which look like gravity. So that's one of the things we're looking at right now. So it's an interesting path because it allows us to describe physics based on the information that observers can obtain about particles through these influence events. A lot of the quantum mechanics, actually, this results in some interesting quantum mechanics. When you have a particle here, and say this particle is influencing these two observers, one of the difficulties is that if the observers, they can record when they've been influenced. So P knows when it's been influenced, Q knows when it's been influenced. But if P and Q get together and they compare notes, they can't reconstruct what the particle did because Q can't know whether it was influenced before P and vice versa, because this is the partially ordered set. So there's no way for any observer to reconstruct what the particle's done. So you have this concept of information isolation. There's not enough information obtained by any observers to reconstruct what the particle's doing. And this idea of information isolation is a critical idea in quantum mechanics. And it arises naturally in this picture. Here you have, here in this picture, if you work out the space-time mechanics, the particles observed to be zigzagging back and forth at the speed of light. And that's a relativistic quantum effect called Zitter-Bevegan. And that's a kind of an interesting thing. If you can actually imagine if you treat a particle zigzagging back and forth at the speed of light, if it has equal probabilities to go right as it does left, the particle basically stays at rest. And if it becomes more probable to go right than left, it'll slowly drift. And this is basically velocities. Macroscopic velocities are then basically drift velocities. What's kind of fun there is you can then think of this as an entropy, because you have a probability of going right or left. The object has an observer-based entropy. So right now, this entropy is maximum because it has an equal probability of going right and left. So here's a system with maximum entropy state. How do I reduce something's entropy? I have to do work on it, right? Throw the thing, and what happens? It moves, and that motion is the motion state with respect to the observer is a state of reduced entropy. So you can actually think of motion in terms of statistical mechanics in this theory, which is kind of interesting. So I'm very interested in information physics and the role that information plays in physics, and I think it plays a critical role. And I expect that the physics of the future will look a lot like your ecology theory, and it'll upset a lot of physicists.
Ecosystems would look more like physics.
Well, they'll look like each other. I think this is basically inference is what's going on here.
Okay, now before we open it up to questions, we could Okay, so I just made this on behalf of Teddy while I briefly talk. So Teddy, as I said, sends his regrets. He is ill and therefore couldn't be here, and I know was very sad not to be here with all of us. Most of us know Teddy from many conferences, and of course it's unfortunate he couldn't be here. So he had wanted to talk about how to update an incoherent personal probability with robust Bayesian algorithms. And basically the short description of that is the traditional De Finetti distinction between coherent and incoherent degrees of belief is dichotomous. Moreover, for coherent degrees of belief to remain so in the face of new information, priors are updated with new information using conditional probabilities, typically guided by algorithms like Bayes' theorem to produce posteriors. And so in some work with Mark Shervis and Jay Cadane, Teddy has adapted the theory of the rates of incoherence to indicate how to apply Bayes' algorithm even with incoherent degrees of belief. And so this is the reference to more paper if you're interested in that, but I thought it was important to mention that. And one key thing about this paper is that importantly they show that the incoherent agent doesn't need to know just how incoherent he or she is in order to partake in the process of the self-improvement that comes about through the algorithms or the theory that he derives. So anyhow, that's just a brief mention on behalf of Teddy. And so now let's, why don't we open it up to discussion, questions? Duncan.
Well, I wanted to ask Richard a question. One of the things that I've come about this is about causality, putting causality and independence in the center of the research program. Independence is a knife-edge property of joint probability distribution. So you take a joint probability distribution that's independent, and you perturb it in any way, and you don't have independence anymore. And I guess one of the things that I feel I learned from James in this whole discussion about entropic points of view is to be very skeptical, I don't know if the right word is skeptical or questioning of these knife-edge concepts. So how meaningful is the concept of independence as a foundation for causality if it's subject to this highly, to the fact that it's not structurally stable and it disappears if you perturb the joint probability distributions just a little bit. And I guess the second question is, does that mean that maybe is there a statistical conception of causality that might be more robust?
Well, great question. So on the conceptual side, I think it's perfectly sensible, and I think when you look at how most scientists understand causation, it's through some image of a randomized clinical trial where there's a random assignment of treatment. And the fundamental assumption one has to make there is that however you randomize, it's independent, right, of other things that might influence treatment, right? So
Your basic model is that type of model?
That's not my basic model, but I'm saying,
Well, you're saying that's the model of causality that you're working with.
that I think everybody would agree at some level is the foundation of conceptions of causality in medicine, in economics, etc. But we can talk about that later. But what I'm just going to say is that on the other side of the coin, you have the perspective in which everything is connected to everything. So there's not going to be any independence anywhere when you really look fine-grained enough, right? Which I think is difficult to argue against, especially when you look at sort of fundamental physics. So at some level, on the macro, right, that we do in social science, right, it's all an approximation, and there is no independence anywhere. Right? But what we found is in domains ranging from genetics to brain imaging to education research to economics to a whole bunch of other domains, if we take this approximate view, right, and we use independence as an inference to causal structure, right, and we have to do statistics to figure out what's approximately independent and what's not, right, we get consistently good results about how to predict what's going to happen if we intervene, but we did not get that before. So I think that there's a number of other issues about the whole project of sort of, connecting causation to independence that are difficult to really put into crystal clear relief. But I don't think it's disputable at this point that there hasn't been a lot of really success stories that we don't really know how to explain in any other way. So,
What about the second
Duncan,
part of
I'm
my
sorry,
question?
sorry, but I mean, we want to,
Yeah,
if
sure.
we can
Okay,
have
okay.
a general discussion, and if there's bilateral discussions, we can save that. I think Ilya had a question, and then we'll come to Ariel.
Just something about what John talked about. So in your last slide, the last slide you're talking about the general philosophy of how theories are going to look like based on maximum entropy. And I genuinely agree with some of what you're saying, but I want to just make a correction, right? So in physical systems, we know the entire statistical physics is equivalent, can be formulated using maximum entropy models. That's maximum entropy approaches. That's easy. We know that. And much of statistical physics is about problems with multiple scales, but with not very well separated time-space scales, right? So what is vapor transition or magnetic transitions or even the last Nobel Prizes of a month ago, right? They're all about problems with cascade of degrees of freedom and not a very well separated sort of microscopic versus microscopic variables or states, right, in the system. And yet the approaches work beautifully because the entire statistical physics can be written in terms of maximum entropy approach.
So you're saying turbulence, for example, could be
Turbulence might
addressed.
not be. We don't know whether turbulence can or cannot be, but the existence of the cascade of degrees of freedom, the whole spectrum rather than those 2 points, high frequency and low frequency, exists in many other systems.
Do you have to
differences?
conceptualize the system then as a cascade across a set of multiple but discrete scales? Or can there be a continuum?
It doesn't really matter that much, right?
Doesn't matter. That's
Doesn't
interesting.
really matter that much, right? So the issue is, I think, why sometimes we understand sort of the systems and why we do not in other cases, is that there exists fundamentally a lower dimensional, reduced dimensional description, right?
Mhm.
Why does it exist? We don't know, right?
Yeah.
But it does, right? And so in some of these other systems, but it does not, or at least doesn't appear to exist.
That's very interesting.
Right? But we don't know why. Right? And why? I mean, I have, of course, my own ideas. Everybody else in the field has their own ideas, but I don't think that it has much to do with the existence of well-separated scales, because reduced descriptions can also exist for the cascades. Right? That's
Thank you, Ilya. Ariel, why don't we collect a bunch of questions, and then we'll let the panel, as a panel, respond. Ariel, do you have a thought?
I feel like a deer in the lights of a car that's coming out. Because now I was going to address those issues, and now I want to address this issue, and all over the place. But I've heard 2 or 3 remarks that are absolutely conciliant with the way I think about these things. One had to do with independence. Quite apart from whether we deem 2 variables to be independent or not, the considerations of independence are absolutely necessary if ever we're going to be doing science. Because no matter what kind of problem we're addressing here, we have to accept that whatever is going on in Andromeda is not going to be affecting it. Otherwise, we just can't even get started to do science. So the issue is not there is a physical mechanism that makes events in Andromeda independent of what's going on here. Now, that has nothing to do with reality. It has to do with the pragmatics of building theories. We need to have theories that are useful. If in order to make any prediction about anything, we have to consider the whole universe, then it's a non-starter. So we have to have independence somewhere in the very beginning to build models.
can you answer my questions in the future too?
I'm sorry?
Just answer my questions for me in the future too.
Now, the one interesting, I really thought of one thing that you said that was very, very interesting. Even if you start with things that are independent, the moment that you lose information, that loss of information screws up the independence, everything starts being a little bit correlated, and this is a highly non-local.
It's conditional independence. So it's not independence, it's conditional, which is a different thing.
But isn't it interesting that the theories that we consider to be most fundamental in physics, like quantum mechanics, are highly non-local.
Yeah.
And they involve probabilities. In other words, we don't have enough information there. So that's why I was wondering, is there any way to quantify the propagation of this loss of independence, or rather the propagation of this appearance of non-localities in your networks? Would that look like a quantum system?
That's a great question.
Okay, let's take another question here.
So I actually want to comment and back a little bit on your comment about things happening to the independent, and also relate that to modeling turbulence. It is sort of very basic and fundamental to separate problems into independent parts. That's very fundamental. But there are problems where that doesn't happen, and a very simple example is the multivariate student-t distribution, where each dimension, if you try to separate it, they don't separate into independent, and you can't just multiply them to get multivariate.
Mm-hmm.
But there are other ways to separate the components that are nonlinear, and you can define essentially a generalized product and a concept that's related to what Salas calls Q independence as a way of separating the variables and defining exactly what the nonlinear relationship is between the dimensions. And that whole framework has become a way of modeling problems like turbulence, where you can't assume that the microdynamics behave in a purely chaotic way, which is sort of the underlying assumption of ergodicity and the other basic elements of the maximum entropy approaches. So I think there are other ways of looking at these problems, and they do relate to some of the issues you brought up about complex systems.
Thank you. So I'm going to use my moderator's prerogative just because I'm guessing that the remaining 10 minutes will be taken up with the panel answering and addressing all of these great questions. And I had a question as well, which was related to Richard's discussion. So, we learned that at times we have to deal with the loss of information, and that loss of information then induces a potential breakdown of notions of conditional independence. And I work a lot with survey data, and one of the things that I think about when people construct surveys is that we have to deal with a trade-off between the kind of loss of information that comes from, for instance, a question asking people to specify a probability. What are the chances that the stock market will go up by 10% next year? And we know that the response that's going to be given is going to have all kinds of measurement error. There's lots of evidence of focal pileups, et cetera. The alternative to that is to provide buckets, some kind of Likert scale that says, okay, very high, high, modest, very low, and low. Does information theory give us anything to recognize or think about the trade-offs between what kind of loss of information would be preferable or would be better for thinking about inference generally or causal inference? So anyhow, with that, but with all the other questions as well, let's open it up to the panel.
Can I just address that's a great question, and there's a whole field of psychometrics you probably know, right? And I think the deal there is, if you have a quantity you want to measure, and you know that if you have a single measure of it, it'll be noisy. If you ask many questions or items that measure the same thing, you can actually gain information back. Yeah. And then the problem is if your conception of how those different questions, right, all covary is wrong, because you assume that they're all covariant because of a single thing they're measuring. But if they might be actually independently, right, measuring something else, or they might interact with each other, then you lose information back out again. So there's this really interesting fine-tuned balancing act going on, where multiple measures of something will gain information unless, right, they're not covariant because of this common thing. And how to detect that is another project that I've been working on for about 5 years, so I'd love to talk about that at a different time, because that's a great question. I mean, there's this, in the field, just to finish, there's this really interesting question of the more measures you get, right, even if they're all very weakly associated with the thing to measure, the more information you get cumulatively about the thing to measure. But right? If they're not actually all covering about the same thing, you lose. So it's a very interesting trade-off.
May I follow up on that? Just a curiosity question. When I don't observe a variable z, I know several ways to try to guess it. One is factor analysis, proportion psychometrics, to find z such that x and y are independent conditional given z. Okay, this is one way. Another way, if I observe z with error, I can try to do deconvolution to recover the expression of z. Is there something as using these two ideas together?
Okay, can we
Sorry,
ask,
sorry, yeah.
can we ask other members of the panel just to weigh in on various aspects of this very interesting conversation?
I'd rather hear other questions.
Oh, okay. Anybody else want to say anything?
Well, I guess this makes me wonder. So I mean, one of the problems with the continuum is in reality you don't ever have enough resolution to resolve a continuum. So how is this related to that type of problem? I'm wondering.
Well, that's a really great question. If it turns out that, you know, the way you bin in a Likert scale, right, is the right approximation and distribution, right, then you can recover all you need to completely. But if there's some funny things going on in the distribution of the original thing you're trying to Likert scale, complete chaos can happen. So you have to make an assumption about the underlying quantum, a continuum thing that you're actually measuring, and that's a complicated discussion to have. But I mean, I think that permeates all of science. Right?
Can we hear other disciplinary perspectives on some of these topics?
Well, I wanted to respond to Ariel's idea that somehow we have to be practical, we have to focus, as it were, and issues of independence and dependence, right, have something, if I got you correctly, to do with our subjective motives, as it were. But it seems to me there's a, I don't know, you know, which came first, the chicken or the egg, about this, because the fact that we can.
That's a question for John.
Yeah. Okay, good throw. It seems to me that the issue of that we can ignore Andromeda, right? I mean, that's partly subjective. I mean, if you're an astronomer, you can't ignore Andromeda. If you are a biologist, presumably you can for now anyway. But that also has something to do with, I would think of as objective independence, right? I mean, if I'm studying microbes through a microscope, you know, the world is such that, or the universe, I should say, is such that Andromeda has not very much influence. I mean, it is, quote unquote, objectively independent. So, well, how do you see this back and forth?
Well, there are variables that are more relevant to the particular problem at hand.
Right.
And that's the end of it. And it is very, very difficult to identify those variables. The success of physics is just that it relies heavily on the fact that physics is much simpler than other sciences, in that a few variables seem to do the job. And by a process of trial and error, mostly error, people have figured out a few variables that matter. And there has been success. But it's very pragmatic. It's not that physics reflects ultimate reality in any way. It's, for a particular problem, we worry about Andromeda. For another problem, we don't. And proceed.
But there is something about the universe, some objective features.
Oh, some things
right.
work and some things don't.
Right,
This
yeah.
is the ultimate
Okay.
question about the validity of science.
Right.
Why does science work? Because it works.
No, that's a punt. Come on.
It is, but it's deep.
I'd say it's part of our responsibility as modelers is to define the domain of applicability of the model. And I can remember a long time ago taking physics and learning quantum mechanics, and one of our homework problems was, okay, you want to talk about a billiard ball hitting another billiard ball, figure out what the quantum contribution to that would be. It turned out to be a very small number.
Sure.
It would be safely neglected if I want to hit billiard balls.
Sure.
I think that's your point.
Yeah. Physics is much less fundamental than people think.
Yeah, but
Wishy-washy,
I- this is something I'm hoping we're going to talk about more, which is that this infometrics point of view, which says what you conclude depends on what your informational state is easily confused with a critique of scientific reality or the validity of scientific outcomes. And there's a big difference between saying, well, we don't exactly know how to measure people's attitudes towards risk in questionnaires, and saying we don't believe in global warming. And we've got to find some really simple, hard way to insist on that distinction, I think. And that's one of the things I'd like to hear more about.
No, of course, I agree completely.
That's a very good point.
Yeah, it's actually a great point to end this session with. We're at our time. I think we have a break, coffee break, so we can continue this great discussion.